and gentlemen, so I greatly thank you for participating today's I²CNER seminar series. The I²CNER seminar series was launched in 2010 upon the interception of I²CNER. So since then, seminar series has featured the best researchers in the world on carbon neutral energy issues. So I'm Toshinori Matsushima and I'll be a host today. So as you know, so solar cells can convert sunlight directly into electricity and are therefore very important for establishing the future carbon neutral society by reducing the fossil fuel consumption and carbon dioxide emission. So among many reported solar cell materials, so hybrid perovskites are widely known as the post-silicon technology. So because hybrid perovskite devices fabricated even using low-cost solution processing can have very high solar power conversion efficiency now. So therefore, I²CNER is also investigating hybrid perovskite solar cells. So with the aim of getting even higher efficiency and operational durability and analyzing basic physics on hybrid perovskite films and devices. So today we welcome Professor Miyasaka in Toin University of Yokohama. So Professor Miyasaka received bachelor degree from Waseda University and master and PhD degrees from University of Tokyo. Then he joined Fujifilm Company. So in 2001, he moved to Toin University of Yokohama as a professor. The reason why I asked him to give a talk today is that he first invented hybrid perovskite solar cells in 2009, and I know his recent findings are also very excellent. So over around 10 years, the hybrid perovskite solar cell research has become the most popular and activated in the world. So I think that he's a father or mother of hybrid perovskite solar cells. So I believe that today he will talk about the basic to state-of-the-art research results on hybrid perovskite solar cells. So now I would like to invite our Vice Director, Professor Matsumoto, to begin our session. So Professor Matsumoto, please.
Okay, thank you, Toshinori, and good morning, everybody. This is Hiroshige. So usually Petros will make the greeting at the beginning of this webinar, but unfortunately he is now on the way coming back from Chicago to Champaign, and it is not easy for him to attend this webinar. So I'd like to say a few words before Professor Miyasaka's lecture. So in this opportunity, I'd like to review about the purpose of this webinar. This webinar is started from last year, and we met the COVID-19 situation at the beginning of last year, and I²CNER people discussed how we can continue the seminar series. And the solution is to hold this webinar, hold the interest seminar series in the form of webinar. So this is the very useful method to hold the webinar under the situation of COVID-19. So and the purpose of the webinar is to facilitate interactions and information sharing among research communities by having cutting-edge presentations and also promoting the collaborations. And I think the Professor Miyasaka's work is very cutting-edge work, and it is very suitable for this webinar today. So I appreciate the lecture from Professor Miyasaka, and I'd like all the participants to enjoy Professor Miyasaka's lecture. Thank you.
So I thank you, Professor Matsumoto. So before we begin, so I would like to take a moment to remind you that your question will be addressed after his presentation. So please use the raise hand button or type your question comments in the Q&A box. So when you are called on, please unmute yourself and speak. So Professor Miyaka, if you are ready, so please begin your talk.
Yes, thank you. for invitation to this fascinating conference. My name is Tsutomu Miyasaka of Toin University. Thank you very much for invitation, Matsushima Sensei, Matsumoto Sensei. You know that perovskite solar cells, the work is spread in the world in the variety of application, of course, including photovoltaic power generation, and also LED and X-ray detector and other things. So I was given 1 hour to talk my research field. Because of the limit of time, I like to focus on recent topic of this research field. This is interfacial material engineering. Interfacial indicate the heterojunction between perovskite and carrier transport materials. That area has having many kind of defects that can recombine the carrier and reduce the power utilization. So this is a very important focus of research to improve the performance of solar cell. So, so let me introduce my university, a relatively less known small university, one of the smallest university actually in Japan, Toin University. Toin name is very popular in Japan, but I just insist this is completely no relation to Osaka Toin, famous for baseball game, high school baseball game. We have established many years around the Tokyo Olympic game in Tokyo, so Toin. And the major part of this school is high school. So we established a university later after the establishment of high school. So the high school is a giant, very giant, having I think more than 6,000-7,000 pupils at high school. And university, our number is a kind of 3,000, so only was half. So location is west of 20 kilometers west of Tokyo here, the famous town Yokohama. You know, the Yokohama city is a second biggest city in Japan, more than Osaka, Nagoya, just for information. So, yeah, before starting my talk, I'd like to, the recent weeks, we have a very many disasters in Japan, especially in the Kyushu area. There has a heavy rain disaster there. So some people lost house and suffer from this disaster, increase the health. So I like to express my deepest sympathy for the people who lost things and suffer from this disaster. Also, the pandemic is spreading the world. The COVID disaster is also very serious. And actually, yesterday, I got an email from the university headquarters that some sports team in the university got the case number 47 in a day. You know, 47 students got infected, got infection. Oh my God. So we have to be careful against this pandemic. So as Matsumoto Sensei and Matsumoto Sensei mentioned, this online meeting is a very efficient way to keep our body healthy. So anyway, let's start the work. So this slide shows the introduction of perovskite name. The perovskite was first discovered in the Russian mountain in 1839. The first material was oxide perovskite with calcium titanate. This was a perovskite, name of a rock. And the name is made after the Russian mineral collector, Prof. living up to 1896. And later, almost 40 years later, Dr. Wells group started comprehensive synthesis of lead halide compounds. But this was not oxide, but halide, including cesium, inorganic cation cesium-based perovskite, and ammonium perovskite is an organic inorganic hybrid perovskite. This one is now very popular in application to the photovoltaic. So the calcium titanium perovskite rock is such kind of very dark black color. So that you can imagine also halide perovskite having black color is a good absorber for the solar spectrum. And halide perovskite is a very strong ionic crystal, like a sodium chloride. And here is a structure of perovskite. And I just I wrote this illustration by myself in PowerPoint for the purpose to include this in my book. So you know this was composed of ABX3. In oxide case, this is ABO3, but having a halide as an anion is ABX3. Here, A cation in green, you can see here, is surrounded by 12 anion halide. So by having a very delicate, say, balance in chronic interaction between anion cation. So it's surrounded by 12 anion. So if there is any slight shift in the distance between anion cation, the structure can deform, and that is a kind of phase change. So the perovskite is actually very delicate in case of especially this ionic halide perovskite against the thermal change. And also we found the light ionization exciting this semiconductor also cause the phase change from delta to alpha kind of. So the problem is ionic migration inside the crystalline, and that we have to adjust the tolerance factor of crystalline by choosing the kind of cation anion. So again, this slide shows the ABX3 crystal structure. Here, center is occupied by the lead or tin or bismuth 2+ cation. This is one of the cation. Other cation is organic or inorganic cation A. Here. Only anion is halide, but halide has a very strong negative ionicity. It is very strong. So similar to the salt, the sodium chloride. So this very strong ionic crystal can dissolve into polar solvent like water, not fully, but partially. So also this is very sensitive to humidity in the air. So some case we have to prepare this crystalline under the dry air. Also, polar solvent molecule can coordinate to the central lead or tin cation to make an intermediate complex before forming the crystalline. So also the water in the air can immediately coordinate to the lead to make an intermediate state complex. So by controlling this complex structure, we can also adjust the process of nuclide formation and crystalline growth. This is a very delicate control. And the free process of crystallization is based on chemical process. It's very, very chemical process having many know-hows. So like control temperature, humidity, concentration, and evaporation rate. So anyway, in other words, we can almost freely change the element of crystalline, like a lead, or between lead and tin, and kind of organic cation. If we change the lead 2 plus to tin 2 plus, the color change is drastic from black to orange. And also, this halide is also controlling color, the band gap. The iodine crystalline, iodide perovskite is almost a dark black color. But if we replace the iodine with bromine, color change is drastic from black to yellowish orange. So I don't have time to show similar case taking place in the silver halide, famous photographic materials, because I spent 20 years in Fuji Photo Film Company before coming to Toin. So this is a very popular work for me to work about silver halide. The typical photographic material is silver bromoiodide or bromide, and very sensitive to light. And we can also change the band gap and absorption property by changing the halide composition between iodine-rich composition and bromine-rich composition. So we have many choice to choose to adjust the band gap color by changing the central cut metal or halide composition. Other unique property is light harvesting power is very strong. It's a band gap absorption. That's interesting. It's very strong ionic crystals can work as excellent semiconductor, like a gallium arsenide, silicon. I haven't experienced any kind of that materials having very strong ionicity and also work as a very good semiconductor. The band gap absorption enables very strong light absorption because extinction index is very, very high, 10 to the 5 kind of per centimeter. Okay. So this is one example how we can tune the band gap of these materials linearly by changing the halide composition between iodine and bromine. You can see this excellent linearity that indicate we can choose band gap. This is one advantage is the silicon is a silicon having a band gap of 1.2 and absorbing from infrared to a UV light. But the band gap tunability is limited. Other thing, CIGS can be tuned for band gap, but the range is limited. But this case, tunability is very high. So we can get this orange color perovskite so that it can only absorb the visible light in indoor illumination, LED. So if we focus the sensitivity of this one just to the indoor light, we can enhance the indoor light conversion power efficiency very, very high. I will show in the last slide to show we could achieve the efficiency up to 34% as power conversion efficiency of LED light. This is I think the best power generator for using IoT device to utilize the indoor light. So as the Matsushima Sensei introduced our first paper published in 2009, but actually we have started this work 2005 and 2006 we have started the solar cell, photovoltaic cell making based on the extension of dye-sensor solar cell. Dye-sensor solar cell is TiO2 nanoparticle sensitized with organic dye adsorbed on the surface of huge surface of TiO2. But the TiO2 is working as an electron acceptor, but hole supposed to be accepted by the electrochemical redox agent diffusing in liquid electrolyte. So this device is a junction of TiO2, perovskite, and liquid electrolyte. So we have started this work as an extension of dye-sensor solar cell, and we chose the liquid electrolyte containing the potassium iodide, almost saturated, to reduce the whole of perovskite. And we are believing that the perovskite nanocrystalline can work as kind of a quantum dot in place of the molecular dye. This was kind of our misunderstanding. Later, we know this perovskite can work just like a silicon wafer, just very thick. The plate of semiconductor perovskite can work itself as a solid-state semiconductor. But anyway, we could get the efficiency just of 3.8%, very low. The problem is, because of ionic crystals, the perovskite can partially dissolved into the liquid polar electrolyte. This is the organic electrolyte. So we could not find any way to stabilize this dissolution of the absorber. But we try to make the solid state perovskite by making a junction of TiO2 and the P-type conductive polymer, polyaniline kind of, and mixed with carbon. So we used carbon conductive polymer mixture as instead of using polar electrolyte. This work was presented in the International Conference of Electrochemical Society in 2008. And I don't have a slide here, but anyway, that is the first the solid state perovskite cell reported in the international conference, and efficiency was 0.4% only. So you can easily get the abstract of this proceeding. Actually, we have many citation number for this abstract. So the perovskite photovoltaic started with 0.4% rather than 3.8%, and started in 2006. The first report was 2006, and all solid state one was reported 2008. What happened is this background story is very, very interesting. I think we can perhaps have one book to show the story of the discovery. Well, in short, this guy, Henry Snaith, young researcher, working in EPFL Lausanne, and he was making the dye-sensor solar cell by replacing liquid electrolyte with solid state organic conductor. This is spirometate. Unfortunately, in the world of dye-sensor solar cell DSSC, the solid state one performance is worse than liquid junction one because of too thick mesoporous tin oxide layer. This cannot accept perfectly the liquid solid hollow conductor deep, much sufficient deep into the pore of the conductor. Always the solid state DCSC showed a lower efficiency. And I sent my university's student just after PhD completion to the EPFL. So they became a very good friend. In the beer drinking, whiskey drinking, the pub, rather than doing the experiment together. And they were discussing. And he, Murakami, is also the co-author of this paper here. Yes. Just mentioned, there is very strange materials in our university. The Miyasaka is working with this, tackling this one for application to photovoltaic. The problem is dissolution of perovskite into liquid electrolytes. So in this case, I was doing this one with DSSC, but unfortunately efficiency is low. So possibly my materials can be applied to these strange materials. So he sent his able student. Then he quit working in Lausanne and moved to the Oxford University to have a position there. And this is his able student and Mike Lee. And he decided to send Mike Lee to my laboratory Toin to spend 2 months for training of how to make a perovskite film. And after 2 months, he couldn't find the solution to stabilize materials. But later, he was working in Oxford by using a spirometer as a solid organic whole conductor, and suddenly got efficiency 10%. Strangely, by using the mesoporous alumina, it's an insulator instead of using TiO2. So this is very strange. The perovskite was placed on alumina. Alumina is separating the electrode and the perovskite. But what happened is alumina is working as kind of scaffold to support the perovskite crystalline. And perovskite crystalline is filling the pores of the alumina inside to touch the conductor electrode. Then alumina is not necessary. That is just the supporter. So they found the efficiency 10.9%. So when this paper published, almost no one was interested in this material because of 2 points. Very strange material, strange, and low efficiency, and poor stability. So this kind of things, no one takes special interest to follow the work. But ironically, this world, if efficiency exceeded 10%, so people can start interested in applying this one. I have some story before, why we have started this work. That's the real start of this work is my establishment of my university venture company, Pexel Technologies. That was established in 2004. And this was a typical venture company in Japan because financially it was fully supported by university, and Yokohama City also supported us. And we didn't need any money to have the room and so infrastructure, power, and what. But we need a young researcher. So we recruited a young researcher by publishing paper of our company. So one guy came from university, Tokyo Polytechnic University, Tokyo Koge Daigaku, and his name is Teshima. He was actually working on perovskite, but for application to light-emitting two-dimensional materials. 2D is the quantum confining effect. 2D materials has an X-ton. X-ton can emit very strong luminescence, but there was no way to apply this one to photovoltaic because the materials have very strange, sharp absorption, not broad absorption. So they were only interested in application to the nonlinear optics. But Teshima introduced me. This Mr. Kojima was an able student, and Kojima was interested in applying this perovskite for photovoltaic. So he was belonging to not Toin but other university, but I accepted him. Please do experiment in my university. So he was making perovskite cell in my laboratory in Toin. So I didn't know nothing. I didn't know anything about perovskite. So this guy brought perovskite in my laboratory. So I was very flexible in applying any kind of photo function material for application for the photovoltaic. So fortunately, we found the ability of these materials for light excited current generation. So that's the first start of perovskite work is the establishment of university venture company. Other interesting thing, our university is private, not like Kyushu University, and the tuition is very expensive. And I solicited Kojima to join in the university, but he said no. He was engaged with a company employment. But fortunately, I got a position in Tokyo University for guest professor 5 years. So I was able to recruit a student. So I suggested him come to my laboratory, not in Toin, but Tokyo University, to continue the perovskite photovoltaic. So he finally said yes, kind of 50-50%, because going to companies are earning money, going to the university they're paying money. So anyway, he accepted. This is my fortunate story. So I will some people published this story this year, maybe by Bunge Shunjusha. Complete book. This is a non-fiction writer with introduced my work. Okay, so this is 2012 paper triggers the world research of perovskite. Here's the 2012. From 2013, it's a boost of publication paper. Main player was unfortunately not Japanese, but China. Chinese papers were so much, and this is followed by USA and Korea. The work was started in Japan, but the very quick follower was outside Japan. So this is typical structure of perovskite. Here we have a perovskite layer sandwiched between the electron acceptor and hole acceptor sandwich, and which is very thin film, typical thin film cell. Here is a spirometers. Henry Snaith was working this one for application to DSSC in Lausanne EPFL. So now he applied this one as a pole conductor and to achieve 10% efficiency. So this black color is perovskite iodide, the methyl ammonium lead triiodide. And this gold was a gold electrode, counter electrode. Only counter electrode is a vacuum deposit. It's not necessary to use this one. The cheapest one is a carbon, but we can change this one. But in the laboratory, to guarantee the safety and stability of perovskite against corrosion of metal. So many people are using gold as a counter electrode. What about the spectral sensitivity of perovskite? Here we can see the silicon cell having a very broad absorption, but it is an indirect transition. So the extinction coefficient is rather low. The champion excellent semiconductor for photovoltaics is the gallium arsenide here in blue color. Yeah, excellent because it's a very steep banded absorption. The cadmium telluride is also excellent, but unfortunately, use of cadmium is not allowed in Japan. No industry is using now cadmium. So when we try to insert a line of perovskite in black, this is perovskite. Immediately we can compare this one, perovskite, with gallium arsenide. Difference is in absorption start. Absorption start perovskite at 800 nanometer. The gallium arsenide is 900 nanometer. So this is a gap of 100 nanometer in band gap. So my dream is to achieve the band gap absorption similar to the gallium arsenide. With a single cell, this gallium arsenide is able to work with 30% efficiency with a single cell. This is excellent, excellent. And perovskite now 25%, also excellent. But I very much hope someone can achieve the perovskite device working similar to gallium arsenide performance. So everything is nice for gallium arsenide, except one, which is high cost. It's almost impossible to apply gallium arsenide for large area power generation purpose for many years. Almost impossible. This is available for space satellite or a CMOS device for the information transport, the IoT device. Other excellent performance is light absorption extinction index. It is 1 order or 2 order factor higher compared to crystalline silicon. The crystalline silicon here, the perovskite here. Because of indirect transition of crystalline silicon, this absorption index depends on the photon energy. The visible reason here, you can see the gallium arsenide perovskite, the absorption power is almost 100 higher than. This indicates perovskite of light absorber can work with very, very thin film, approximately less than 1 micron thick film. The silicon wafer is a minimum 100 micron thick. Is a industry workable thinnest layer. So you can imagine the silicon is a 100 micron. Perovskite is a 0.5 micron, very simple and very light in weight. So this is an ENER's table showing laboratory efficient solar cell development. So the perovskite is now here, in the yellow. So very quick improvement in enhancement in efficiency. Now it reached 25.5%. Silicon is 26.1%, almost a comparable. So perovskite by now surpassed efficiency of CIGS, and cadmium telluride. They are competitor with silicon, and perovskite exceeded this efficiency. So next generation cell, the perovskite solar cell is the only one solar cell that can compete high efficiency with silicon, with the exception of gallium arsenide. But gallium arsenide is impossible to be commercialized. So when we focus on the perovskite efficiency progress, this was showing this graph. The first solid state one started in 2008 with 0.4%, and the liquid junction one published in JAX paper 3.8%. Okay, now it's 25.5%. It's staying almost 2 years, achieved by Korean group. And next direction, what? Now people is developing the tandem cell to further enhance the efficiency. Tandem cell with silicon or CIGS. But other direction is to change the composition perovskite, typically by eliminating the environmentally hazardous lead, or by eliminating organic cation because of low thermal stability. So actually, I'm now leading Kakenhi S project, focusing on the all inorganic perovskite and lead-free perovskite, rather than making a tandem cell. Tandem cell is the work of, I think, the company rather than the university. But it's okay to challenge tandem cell making as a perovskite engineering work. So this is a so-called photocurrent density voltage curve, JV curve. And when we make a cell, we are scanning voltage by measuring photogenerated current to make this check this characteristic curve. Here, a very important parameter is the photovoltage. Here, open circuit voltage. Photovoltage is determined by, first, the band gap of semiconductor. Here, band gap. But according to the second rule of thermodynamics, any kind of the power conversion should be accompanied by thermal loss. No perfect conversion present. In case of photovoltaics, here is a thermal loss, and our obtaining photovoltaic is always much less than band gap energy. Here, the electron acceptor can accept the photoexcited electron. The whole conductor accepts a hole from the valence band. Actually, the short circuit photocurrent is saturated for, I believe, for all kind of photovoltaic materials, including, of course, silicon and organic thin film solar cell, dye sensor solar cell. Short circuit photocurrent is almost 100% quantum efficiency. So this kind of smartphone having photo detector here, silicon based. A quantum conversion is 100%. It's easy to convert the light energy to the photocurrent at 100% efficiency, but this is only to produce a photocurrent, not voltage. Very strict thing in power conversion. We have to get the open voltage plus photocurrent plus high fill factor here. So this is to minimize the internal resistivity of device. So this is typical scheme of photo-excited carrier transport. This is, we have here methyl ammonium lead triiodide having this band gap. Band gap is a kind of 1.6 eV. So this sandwich between the electron transport layer ETL and the spirometer is a whole transport layer. The obtaining of photovoltaic is actually 1.1 to 1.2 with respect to band gap 1.6. This is the highest photovoltaic 1.225 we obtained. But in case of perovskite, as I showed this inside, the loss between voltage and band gap is kind of smallest in case of perovskite. So here, we can hear the gallium arsenide. This is a nice, very, very nice semiconductor. I always remember the band gap is one band gap is 1.42. The highest photovoltaic is 1.12. So loss is almost 0.3 electron volt. But perovskite is also excellent, having a very small loss in thermal loss here. Other photovoltaic cell is not good. Silicon is worst. See, this is also not good. So our task is to minimize this thermal loss to enhance the global power conversion efficiency. Fortunately, perovskite is gifted by the nature's so-called defect tolerance. Actually, the perovskite crystalline is made by solution process chemistry, not in vacuum deposition. So we can imagine how dirty the surface of the crystalline layer and bound granular, having many impurity defect. But it's very hard to find. This kind of defect is tends to be formed at a very shallow state. In silicon gallium arsenide, materials should be made in a very, very pure state, 99.99969 purity, because the defect tends to be formed in very deep state in band gap. But perovskite case, the defect is very shallow. So if the carrier once trapped by defect, it can be detrapped at room temperature, like a zombie semiconductor. So this is very fortunate property in physics of perovskite halide. And also the conduction band is formed by antibonding of lead p orbital, and valence band is also antibonding orbital of s. This is opposite to gallium arsenide case. Gallium arsenide conduction band is s and valence band is p, and in perovskite it's antibonding. It's also related to why this defect tends to be formed close to the conduction valence band. Okay, next slide is to show the coating of perovskite by speed coating method. So you will see first the source materials in solution is transparent, colorless solution, and the spin coating is to make a very, very thin liquid layer film. It's immediately evaporated to deposit and crystallize the perovskite nanocrystalline on the surface. The once crystalline is formed on the plate, we can see the color change. But if it's exposed to UV light, we can see a very vivid the photoluminescence. Let's start. Now we're dropping the source materials and the speed coating is started. Immediately evaporation started, leaving the nanocrystalline perovskite. The under UV light is emitting visible light, green color. It finished only 20 seconds. In short, the solar cell is now made. So in laboratory, solar cell making is very, very simple. Next day, this one, the substrate was alumina, not TiO2. if we change substrate to conductive electrode, this PL is converted to current generation. And we also capped this material with silver or gold as a counter electrode. So in photovoltaics, high efficiency and the lifetime of excited photon is a sign of high efficiency in power conversion, because the excited state electron is very, very stabilized in long lifetime. In long lifetime, it can diffuse in a semiconductor, finally trapped by electrode to generate the current. But current is easy to be generated. But how we can get the sufficiently large voltage, this depends on how we can minimize the defect. This is a shallow trap in the band gap. So it's a popular recombination, the Shockley red hole recombination. It's a trap assisted recombination. Where is trap? Trap exists on the surface of nanocrystalline or the interface between the carrier transport layer and the perovskite. So to explain this one, I'd like to shortly summarize. Superiority of perovskite, high photovoltage, intense light absorption, tunable band gap, and it's a very, very low cost. How much? The perovskite film of 1 square meter is cost like $1 to $200,100円から200円ぐらいしかしない。非常に安い。It's also printable, and we can also use an inkjet printer. But the challenge is the thermal stability. Because of having an organic part, it can be マッチで火をつければ燃えちゃうこともあるので、we like to ensure high temperature, 200 degrees Celsius. Also, lead is a problem. 鉛の問題があるので、鉛もできれば除きたい。これが大きなチャレンジですが、これについては後で話しますね。Okay, this recombination, the impact is, if the recombination involved, this can be seen in the reduction in the photovoltage and also a fill factor. Okay. So to assess this recombination loss, we are measuring the dependence of open circuit voltage on the intensity of light. Okay. This intensity light is a logarithm, not a linear scale. So the equation shows we are supposed to get the linear dependency, this one. And from the slope, we can get so-called ideality factor, N, ideality factor, that indicate how the VOC is stable against the change of light intensity or against the reduction, decrease in light intensity. Yes. So how we can decrease this ideality factor? One strategy is to get a large grain of perovskite. This indicates to reduce the grain boundary area. Because surface is occupied by a trap with some density, and increasing the size automatically reduce the surface area of the crystalline and leading to reduce the trap density. Let me show some example. This is a very nice view of perovskite cell on the sectional view of SEM. This is a so-called multi-cation lead mix halide perovskite. This looks very complicated structure, but this is one of very stable crystalline under room temperature without causing the phase segregation, so-called phase segregation. And we developed how to make this one under ambient air with relatively low relative humidity. If humidity is too high, the water can coordinate to lead to make to disturb the complex formation of intermediate. But with this is to reduce factory instrument cost reduction. Can avoid to use a dry room in the factory for mass production. So this moderate humidity, we can make high efficiency structure. How? By adjusting the recipe of crystallization to make this large grain and smaller grain boundary area. You can see the grain boundary area is running vertically, not parallelly. So if any defect resided here, still the carrier can be transported directly via a grain. Almost surface relatively flat. It's a very necessary thing. So if we succeed in making this one kind of thing by changing the grain size, the grain size is very delicate to the surface composition. We try to dope potassium on the surface of TiO2, not perovskite TiO2, to control the crystalline nuclei formation. The nuclei number is low, we can enlarge the size of perovskite grain. If we succeed in making this one, we can get efficiency exceeding 20%. And here, the quantum efficiency against the external quantum efficiency, the photocurrent generated per instant, not absorbed, instant photon number, so 90%. Do you think it's very nice, beautiful curve? So we can imagine the internal quantum efficiency also unity 100%. The ideality factor is 1.3 that indicate at the low intensity we can still get the photovoltage close to 1 volt. So the 1 milliwatt per square centimeter corresponds to sunny day sunlight. The rainy day, cloudy day, the intensity is maybe 1 to 5 here. For the case of silicon crystal cell, that is hard to work in a rainy day because of a big drop in voltage. Photocurrent density is normal, but dropping. But gallium arsenide perovskite, it still be capable of producing high voltage. So, I'm sorry, I spent 1 hour. Be patient to listen to more several minutes. The passivation is to improve the interface by minimizing defect. One method we recently challenged is use of mixing material. This is titanium carbide having 6 atoms layers. We inserted this one at the junction of perovskite and TiO2 as a blocking layer. This is very summary stable one. And we intentionally oxidize this mixing to so that it can have some semiconductivity N-type to rectify electron transfer. So by inserting this one between the ITO and perovskite, now we don't have any TiO2. It's a TiO2, the semiconductor-free planar cell. The mixing layer is very, very thin, but it can working as a whole blocking layer and any type semiconductor. So we can enhance the efficiency up to 18% with the planar cell. Postdoc Kim, now he's now working in Korea. He was challenging use of germanium doped into lead to passivate the surface between the TiO2 and perovskite. It also tends to change the grain size, and very small amount, 3% germanium. On our chemical analysis, it's coating the surface of the perovskite grain as a germanium oxide monolayer, and this can also passivate a defect. So the result is enhancement in the VOC up to 1.18 volt. This voltage is one of the highest voltage obtained from the narrow band gap perovskite absorber. So by getting this voltage, we can get a 22.5% efficiency. Okay, next topic is all inorganic perovskite we are now tackling. Why all inorganic? Because thermal stability is highly improved because of the organic free structure, and this is a strong point. The thermal stability can reach above 300 degrees C. What are the progress of the study? The all inorganic cell, cesium lead iodide. Do you remember the first discovery of the halide perovskite took place in the turn of 19th century, 1 century before, but no one tried to apply this one for photography. But now many people are working with this cesium lead halide. The first study published to 2016 showing efficiency 4%, very low, but now it's slowly being improved. But problem is a very large thermal loss between band gap and the photovoltaics. So we are now interested in reducing this loss. So what kind of say halide? We chose the iodide bromine mixed halide, and the mixed halide also show the spectral sensitivity dependence on the composition of the halide. Yeah, and if we use the pure iodine, band gap is 1.6. It's sufficiently. It's low enough to absorb all visible and near infrared light. If we work on chloride, band gap too high. So bromide is also too high to harvest visible light. What I chose was I²BR. This has a band gap 1.9. A little bit higher than the visible light, but it's enough to work for indoor light absorber. So this was combined with a polymer, conjugated polymer. It's a dopant-free P-type polymer. This was given from Mitsubishi Chemical. We are now collaborating with Mitsubishi Chemical. Mitsubishi Chemical is very, very close to this place, just 20 minutes for a bicycle. Fortunately, this polymer worked very nice. And we could first get the efficiency 14% with voltage 1.15, but we further tried to improve this one by changing the TiO2 with tin oxide, the electron transfer materials. This is not popular tin oxide, but the surface is capped with amorphous tin oxide. Yes. Amorphous tin oxide is coated with a precursor tin dichloride, and we intentionally oxide this one under the air before coating. The coating solution is aged under the air 4 days, and the partially tin 2 plus is oxide tin 4 plus by increasing the electronic conductivity. So this precursor was coated on the top of the perovskite layer. And here, the IB curve, if we coat the mesoporous tin oxide only, we have a poor performance, having a huge so-called hysteresis. But by modifying the surface of tin amorphous layer, you could get high performance. I have to explain something, because the amorphous tin layer is necessary to perfectly coat surface of tin oxide to cap any physical void defect. But the amorphous layer is an insulator. So if it's too thick, it can have a very high resistivity, and the device is not good. So we have to adjust the thickness very, very thin, possibly less than 5 nanometer by solution process. Then we can accept the tunneling of electron and blocking the hole. The result is very high voltage, 1.42 volt. I was very much surprised to see this voltage with single photovoltaic cell. Band gap is 1.9. There is still a loss in the less than 0.5 volt, but I have never seen this high voltage from a perovskite absorber. It's published in JAX last year. And our paper, the first paper shows a 15% efficiency, but now, just a month ago, our next second paper accepted advanced functional materials, so our efficiency improved to 70.4%. And then in Tsukuba ICE, we got a certified efficiency with VOC 1.42. So this is a certified photovoltaic, very, very high. Durability, shelf life durability is also sufficiently high because of all inorganic. So this paper just published, and sunlight efficiency is 70, but indoor efficiency reached 34%. This is a raw data, and you can see indoor that 200 lux and 1,000 lux, the VOC is still maintaining over 1.1 volt. I'm also surprised this one. Oh, so high voltage still exists on the indoor light. Indoor light is almost intensity is 1/1000th compared to the sunlight, microwatt. Actually, in consumer electronics, this is a device to pump up the voltage up to 4 volt in order to store the power to secondary lithium-ion battery charging voltage 4.2. If we could get the VOC voltage 1 volt, so now this device can charge the lithium-ion battery by using external circuitry. So in comparison to silicon and other cell, the perovskite is best cell for indoor application. And you can see how the indoor application can be. I'm sorry, I will finish next 5 minutes. Flexible device, you can so easily imagine. We are also making a flexible device starting with a 125 micron plastic film as a substrate. And this is mechanical stability by against the bending of the cell up to 1,000 times, almost small PEC loss. Recently, we could find some malarian drug can also passivate the surface of perovskite and TiO2 to boost efficiency to 24%. This is the highest efficiency for plastic film solar cell. And other application, the semi-transparent perovskite can be available for window attachment. And the space application also was now becoming very promising. We are doing a collaboration with JAXA for recent 5 years. And then what is necessary is to ensure high durability against the impact of temperature change, -80 to +100. Also, the high stability against the energetic particle irradiation, electron irradiation, proton irradiation in order of 1 mega EV or kilo EV, very high. This can damage all kind of the ceramic, including the silicon solar cell. So we have tested such solar radiation stability and found that the before and after the performances didn't show big change. So this is a difference in the perovskite composition. You can see a dose of up to one order of 14, 10 to the 14 particle radiation almost didn't destroy the perovskite solar cell. And this is the result. The cell can survive up to 10 to the 15 dose of proton fluence. And this level actually destroys silicon and gallium arsenide cell in space, on the space satellite. So perovskite thin film is more stable, more tolerant than commercial photovoltaic cell in space application. And this work is reproduced by other group in the world, especially the German group, München University group also shows. Now we are doing a rubber balloon test by burying the solar cell in balloon to expose the solar cell and high vacuum, not very high, but the vacuums and high irradiation of UV light to check the durability of the solar cell. And just say a month ago, this balloon was launched in Hokkaido at the highest, almost 30 kilometers above the sea level. And almost this atmosphere is almost nearly vacuum and exposed to one temperature of -50 degrees Celsius, and our cells survived. And this report we have published in several papers before. And the interesting news in German, the rocket was launched bearing the perovskite solar cell. And this test is now becoming very popular in the world. So space application is not extension of the popular application of perovskite. Okay, I'd like to finish. We could complete a book just with submitting all chapter data a week ago, and Wally is maybe selling this book. The topic is huge. Starting with a background story, how we could discover the perovskite, starting with a venture capital in the university, and also the topics include the X-ray detector, photo detector, and tandem solar cell. I think you can enjoy reading this book. And also, Hawaiian Convention Center is having a Pacific Conference in December. It's a hybrid conference, the in-person and virtual conference. I have to organize a session of perovskite. So if you're interested in checking the conference, please join this conference. Okay, thank you very much. We are doing international collaboration, Taiwan, China, Italy, Germany, Russia, and also India also started. JPS Kakenhi is very helping for research and also just support. Thank you very much for listening my talk. Thank you.
So I thank Professor Miyasaka for your excellent talk. So we can learn many things from your talk. Then we move to the discussion. Is there anybody who has a question to Professor Miyasaka? So please, hands you are up. So Professor Miyasaka.
Matsushima Sensei, you
Yes.
can turn on your video camera.
Oh, okay, sorry. Could you hear my voice?
Yes.
Okay. So, Professor Gamba.
Yeah, any kind of question, very general question about, say, carbon neutral.
Gamba, you have.
Hello?
Yes.
Can you hear me? Hello, Professor Miyasaka. Thank you very much for a very nice talk.
Thank you.
I have a question about the surface modification of TiO2. You showed that you used the potassium TFSI, and then the grain size was increased significantly. And maybe I guess TFSI ions are important, or potassium ions are important for this phenomenon. Could you please explain why grain size was increased?
You're talking about the TFSI?
TiO2. You deposited the potassium TFSI on top of TiO2, right?
Sorry, TFSI.
Yes.
TFSI is
yes, in this slide. In here, you can 26.
26.
Yeah.
Okay. I'm sorry to skip my premise. Yes, TFSI is coming from dopant of spirometate, and lithium TFSI. This is anion, and we, based on the analysis, the sulfur of TFSI is forming bonding between the titanium to the titanium to reinforce the junction between the perovskite and TiO2. This is this actual result based on the chemical analysis, but we can see this is like some indirect evidence how the TFSI can be involved in surface passivation.
Okay, I see. Maybe probably if we use heating TFSI and also sink TFSI, maybe it would work, right?
Yeah,
Okay.
I have one slide, but I maybe takes time to include this one. We published paper in advanced, this advanced function material paper shows the structure of how the sulfur is reacting with the surface of titanium oxide.
Okay. Okay, thank you very much.
Welcome.
Also, I have another one question that almost in the introduction slides, you talked about the photovoltage, and you said that VOC of the perovskite cell is usually determined by the difference of conduction band of TiO2 and also HOMO level of organic half transport material. But for example, in the university-wise, maybe this is not true that because, for example, HOMO level of P dot or PTAA is about 5.2, but HOMO level of C60 is 4.5, and therefore difference is only 0.7, but we can already achieve over 1.1.
I think you are. Okay, I have to try to enlarge. Yes. これ以上大きくならないか。Okay, show me. Yes. Your point is how the voltage is formed. My opinion, the voltage is not pinned between the gap between the whole transport layers materials HOMO and the LUMO level of ETL. But the VOC tends to be determined by between the conduction band of perovskite and whole transport layers HOMO level. So fundamentally, as this slide also shows, the electron is supposed to be injected to electron transport layer as a semiconductor. So it seems semiconductors conduction band also influencing the voltage. But in reality, we can see much higher voltage. It can be determined between TiO2 and so we saw thinking this kind of TiO2 thing, the SNO2 layer is too thin, too much thin to have the bulk property of semiconductor. Typically, if we use a tin oxide here, SNO2 here, that has a very low conduction band level, but still the VOC is not influenced by the, SNO2 level. That indicates this electron transport layer is playing a role of blocking hole, rather than functioning as an N-type conductor.
Yeah, thank you so much. I understand.
Is it okay for you?
Yeah.
Thank you.
Thank you very much.
So his name is Gamba.
Yeah.
So he's now investigating perovskite solar cells.
Good.
Therefore, his questions are professional.
Thank you.
So, Professor, may I ask a question?
Yeah.
So you mentioned the inclusion of red atom is not good. So red free is necessary.
Yeah.
So what do you think, which metal is more promising for fabricating lead-free perovskite solar cells. Previously, I tried to use a tin, very famous one, but obtained efficiency was very low. Half of efficiency measured from lead-based perovskite solar cells. So therefore, I'm wondering, so which metal is more suitable for lead-free perovskite?
Okay, in terms of efficiency, tin is best.
Yes.
No other metal can compete with tin. But the tin issue is low stability against oxidation. And the tin 4+, unfortunately, cannot work as a normal semiconductor, maybe of too high conductivity. So use of tin 2+ is the best way to replace the performance of the halide. If we could almost perfectly stabilize tin 2+ by participating something. For example, the Hayase sensei of Tokyo Dentsu Daigaku no Hayase sensei is now using a germanium as a dopant to stabilize tin. The next one is this bismuth. The bismuth, silver bismuth, is very popular one, and but the top efficiency is still more or less 4 to 5%. And very difficult problem is quality of the perovskite film is very hard to be improved to dense and voidless uniform flat layer. The layer is very poor, like this. But theoretically, this one can work as efficiency above 25% of absorber. The light absorption is direct, very strong. Band gap is suitable. The electron structure is not very bad. So by improving the purity of layer free of defect, we can enhance the efficiency of this one.
I see. So the amount of lead atoms in perovskite film is not so large, I think.
Yeah, I have.
We should replace lead atoms with other metals for 0.4 gram.
I personally think this is very high hurdle to replacing lead with other metals. If we like to have efficiency close to lead-based one, 20%. Other understanding is this is amount of lead the solar panel bearing. This corresponds to only 1 or 2 centimeters of natural soil surrounding our house. Yeah. So the lead is not like a kind of metal like a cadmium or mercury, say chrome. It's an abundant natural source. So by establishing a perfect recovery of the used goods, the solar cell, the industry is hoping to the government or society can accept the use of lead perovskite, because already the inkjet printer is equipped with a lead-based printing head. It's a ferroelectric device. It's a lead including. Well, kind of a century ago, we are eating lead or some sweet candy also including lead. Lead is everywhere. I think also the beautiful shrine in Nara, Kyoto, it looks very beautiful, but on the surface is red. This is very nice against the corrosion. Possibly, by establishing a nice recovery infrastructure in industry, the lead-based perovskite will be accepted industry. The situation in China is more flexible. No one are minding about use of lead in China.
I talked with American guys, so they said lead-free is not necessary in US. Yeah, they mentioned.
So this slide showed the best application is, I think, the car-loaded EV. Many advantage. The car maker needs a lightweight and cheap materials. This is matching the perovskite. And very stable high voltage against the light variation. This car is running a sunny day. It's also running in the high between the skyscraper building, many shade. So much difference, right? But silicons don't work because of big disturbance in the voltage, but it was stable. Next one is we don't have to ensure 10-year stability for car use because the lead acid battery is the same case. It is being exchanged every 4 or 5 years and very cheap. And dealer can perfectly recycle the PVR attachment without emission to the society. So I think personally, this one is very good.
Thank you. So next one is QWERTY. So please unmute.
Okay, can you get me now?
Yes.
Okay. Oh, Sensei, thank you very much for your talk. I have one question or two questions. You mentioned that silicon compared to the perovskite solar cells, that the voltage drop for silicon is much severe, especially on a low intensity light day than that of the perovskite. Can you explain why this common phenomenon of voltage drop in the silicon compared to that of the
here is a case of other high efficiency solar cells defect density. The silicon is not exception. So silicon should be the ingot should be prepared by completely eliminated the defect to achieve the purity 99.9999 more than 691. Because if defect is resided here, the part of the hole and electron trapped, the ones trapped is very difficult to detrap. And the result is reflected in the drop of a drop in photo voltage. And if the light intensity is decreased, the frequency of trapping can increase with respect to the production of excited photon.
Oh, I see.
So it is a very general phenomenon that if people purchase a silicon panel for rooftop, if the sun intensity decreased lower than 10% of sunny days, the silicon panel can suffer a big drop in the voltage that enable the enable to power the external circuit, the so-called power conditioner.
Okay, and the next question is about the open circuit voltage that you mentioned in one publication rising up to about 1.6. I did not get the explanation for such a high voltage. In the publication, you showed 1.6, yeah, something like that.
1.6 losses are still not small. Reality, the perovskite cells, band gap is 1.5 or 1.6 for methyl ammonium lead iodide, and champion voltage is 1.2. So loss is 1.4 now, or less. This 1.4 EV loss is sufficiently low, and much lower than the case of silicon. And the best, the champion in terms of the small loss in loss is gallium arsenide. Because VOC is 1.12, gap is 1.42, the loss is only 1.3. And this 1.3 loss is close to the shock requirement limit, the engineering limit.
Oh, I see. So knowing that these three factors, the short circuit photocurrent and the open circuit voltage with the field factors, in order of preference, which one is more important to improving the efficiency of the device?
Open circuit voltage.
Yeah, the open circuit voltage, yes.
Yeah, and in reality, that the JSC is easy to get as a maximal level. Yeah, almost all kind of photovoltaic cell are getting the saturated JSC. Almost as dye sensor source and organic thin film. But the field factor, this curve, is we have like to have a more square curve, but the field factor can strictly depend on the internal resistance of the cell. Also, it's related to the level of VOC. So I can show this one, yeah. This one. This direct recombination is rarely happen for the high efficiency cell. So we can almost ignore this one.
Yes.
The problem is here. So VOC is most important, I think.
What does it mean that if you improve the VOC, eventually you are solving the problem of the field factor? Does that?
Yeah, this is linked. VOC level also linked with field factors.
I see. Okay. Thank you very much.
So more question? So Professor Miyasaka, I have one more small question. You mentioned the on page 24, slide 20, so 25. Next slide. So you mentioned when you fabricate perovskite film under the humidity condition, 20 to 35%. So in this case, you can get better power conversion efficiency, high performance.
Yeah, we have in our laboratory a dry room. Humidity zero room. So many researchers is making cell in the dry room.
I see.
But when we publish, I don't know, achieved a high efficiency by making cell in dry room, nothing is special. Nothing is special. And for industry, this moderate humidity process is inviting because was lower cost in installation of machinery. So we or he, that this was this is achievement by Indian researcher. He tried to make the cell this under this condition.
Yeah, because technically I'm today on.
controlling the evaporation rate and how much time we can expose the liquid under the air. So we created a special recipe, but this recipe is not applicable for dry air recipe.
So we usually fabricate perovskite film in a nitrogen filled glow box. So previously, we compare the operational durability of perovskite solar cells fabricated in air and nitrogen.
Yes.
So perovskite solar cell fabricated in nitrogen had better stability compared with air fabricated ones. So
yeah, you can say that.
When you fabricate perovskite solar cell in air, so what is your operational durability?
Operational durability
under sunlight or just putting in air.
Yes,
storage stability.
Yeah. We only checked the operational durability up to 200 or 300 hours under the air. So it was sufficiently stable. Although it shows some drop in efficiency, 10% something.
Yes. Okay, your stability is good.
But anyway, if we make a cell in completely dry room or nitrogen air, the top champion efficiency can be more than the cell made under this humidity condition. Our challenge is to just show the under cheaper environment, we can still get the efficiency beyond 20%.
I can understand, yeah. Thank you very much. So more question? So if nothing, Matsumoto Sensei, may I?
Thank you for finding me. So I wanted to ask one question, very broad question. So thank you very much for a very nice talk, and I learned many things. Particularly, I'm working on metal oxide type perovskite, so I'm quite interested in your talk. And it is quite surprising to see that the perovskite materials can be prepared by wet process.
Wow. Yes.
In my case, always centering it in only the method to prepare the metal oxide perovskite. So my question was that why is it only perovskite, metal inorganic hybrid semiconductor, was found in perovskite type structure? So in the case of metal oxide, there are many different types of crystalline structure. So I'm wondering if other crystalline structure can be available for the metal inorganic semiconductor as well.
Metal inorganic, yes.
Or halide semiconductor.
Yes, halide is kind of limited. No fluoride, but only chloride, bromine, iodide. Halide is limited. A part of halide can be replaced with sulfur.
Yeah.
And metal, actually, metal other than lead has been widely investigated, including antimony, copper, iron, also the titanium, Ti, titanium, and bismuth, and other kind of. So, but I think variation can be enough, but the cation, monovalent cation, cesium, potassium is not effective. Yeah.
What about different crystal structures? For example, in the case of metal oxide, fluoride structure is also available, and also spinel is another choice.
I'm sorry, I don't have good knowledge about. But photovoltaic application relating to this materials is not limited to a perovskite structure.
I think so.
Kind of perovskite-like.
Mm-hmm.
Perovskite-like structure is also under investigation, but the efficiency is kind of 2-3%.
Okay, thank you very much.
So more question? So Matsumoto Sensei, so it's time to close?
Yes, we can be able to close the lecture of Professor Miyasaka. Yes.
Okay, so Professor Miyaka, so we thank you very much for your excellent talk. So
Thank you, invitation.
Yeah, thank you very much. So it's time to close today's seminar series session. So please thanks to Professor Miyasaka again.
Thank you.
Thank you very much.
Thank you very much.